Hello, PyCon. Are you ready to dig into the core of the Python interpreter? So you may not know, Instagram server is a big Python web application, a whole bunch of Python code, several million lines. And my work at Instagram and the work of my team is to make Python fast, to run that Python web application more efficiently. So that's what I'm here to talk about today, how to make Python fast. The goal at the end of this talk, we want to understand why is Python slow and what can we do to make it faster. If we want to understand how to make it faster, the first question we have to answer is why is it slow in the first place? So let's find out. We'll start by checking out the CPython code base. I'm using Python 3.9 for this talk. It's a little bit older, but it's representative of historical Python performance before some of the recent improvements. I'll talk later about how Python 3.10 and 3.11 have become faster. So let's configure Python, build it, and then run some code and profile it. I'm running the Richards benchmark here. It doesn't come with Python, but it's part of the PyPerformance benchmark suite that you can find on GitHub. This is important because there are many different kinds of Python code, many different workloads, and the approach that we take to optimize will depend on what kind of workload we're trying to optimize for. So Richards in particular is an object-oriented benchmark. So it creates lots of Python objects, performs lots of attribute loads and stores, and lots of method calls. This makes it a pretty good representation of many kinds of real-world Python code. I'm using the Linux perf tool to profile this benchmark. Perf is an amazing tool for digging deep into CPU performance. I'm only showing the most basic usage of it here. So after we run perf record, we can then run perf report to view the data from our profiling. Whoops. Okay, perf report gives us a list of C function names ordered by how many CPU cycles are spent in each function. So here we're clearly spending a lot of time in this pyeval eval frame default function. What is that? To understand this, we need to dig into how the Python interpreter actually works. So you probably know that Python is an interpreted language. What does that mean? If we have a simple function like this that takes in some object and returns some attribute of it, Python will compile the source code into a form called bytecode. We can use the standard library dis module to dig into and view this bytecode. The bytecode is just a sequence of instructions that manipulate a stack of values. So in this function, first we will load x onto the stack from our arguments. Then we do a load adder, which gets the x.foo attribute and puts that value on the stack in place of x. So let's say in this case we call our function with some object whose foo attribute has the value 7. So the load adder will load the 7 and put that on the stack in place of x. Then return value just pops and returns whatever's on top of the stack. So what is this pyeval eval frame default function that our benchmark spends so much time in? In a sense, it's the core of the Python interpreter. It's the thing that actually runs the Python bytecode. If we look at a highly simplified version of it, basically it's just a loop over the bytecode with a big switch statement with a case for each possible instruction in the bytecode. So we'll have a case for load fast and a case for load adder and lots more cases for all of the other possible instructions in the bytecode. So that's what Python is doing internally when it's running your program. It's just looping around this loop over and over again, running one bytecode at a time. And in general, this is not quite as efficient as straight-line compiled code would be. Every time around the loop, the interpreter has to figure out on the fly, what am I supposed to do next? What's coming up next? And we have to do some extra bookkeeping to keep track of the values in the stack. Where are we on the stack? Where are we in the bytecode? All of this is overhead. So we can put the first entry onto our list of reasons why Python is slow. Interpreter overhead. Even though this is the first entry on our list, Don't be fooled, it's not going to be the most important one. Profiling showed that our program spends about 1/3 of its time in PyEval frame default, but most of that time is spent doing the real work of the program. Only some of it is overhead. We'll come back to this later. So if interpreter overhead isn't the biggest reason why Python is slow, we need to keep looking. Let's dive in and look at what this loadatter instruction actually does. The implementation of loadatter in the interpreter isn't too hard to follow, even though it's C code. It just does what we said before. First, it gets the name of the attribute we want to load. Then it gets the object off of the stack that we want to get an attribute from. Then it calls PyObjectGetAttr to actually get the attribute from the object. And then it replaces the top of the stack with the result. But this PyObjectGetAttr function should look familiar because it was in our profiling data. There it is, right near the top, taking over 6% CPU time in our benchmark. And that's not all, because the two items right above it, PyTypeLookup and lookDictSplit, are both also called downstream from PyObjectGetAttr. So all three of these, which total over 25% of the time in our benchmark, are all part of this loadatter machinery. So why is the seemingly simple task of loading a single attribute from a single Python object taking up 1/4 of the time in our benchmark? To understand that, let's look at what CPython actually does inside PyObjectGetAttr for the code x.foo. We first have to check if the type of x defines dunder get attribute. If so, we call it. If not, we check if the type of x has an attribute foo that's a data descriptor, and this is where we call PyTypeLookup that we just saw on the last slide. If so, it calls the dunder get method on the descriptor and returns the result. Otherwise, we check if the object x has a dictionary, a dunder dict, and we do a lookup to see if it has a value for the key foo. If so, and this is where lookDictSplit that we saw on the last slide comes in. If so, we return that value. Otherwise, if we have a non-data descriptor, we call that and call that get method and return it. Otherwise, we raise attribute error. So the point is, this is a lot of work that Python has to do for every single attribute load in your program. For comparison, let's consider what happens when a C program does x.foo. In the case of a C program, the C compiler already knows what the type of x is, and it knows what members that type has, and it knows that, say, the foo member, maybe it's 16 bytes into the object. And so at runtime, literally all that has to happen here is a single load from a fixed offset from the address of x. This is a lot cheaper than what Python is having to do. Another way to compare this is to look at the assembly code for the main functions that Python needs to run in order to do a single attribute load in the relatively fast and simple cases. And this is a dump of that assembly code. For comparison, this is the C assembly code for the same operation. A single indexed load instruction. So you can sort of see why the Python attribute load is going to be several orders of magnitude slower typically. So the basic reason for Python's slowness here is that Python is so dynamic, which means we know very little when we compile to bytecode. And that lack of knowledge means we have to spend time rechecking every possibility every single time our function runs. This takes a few different forms. First, we don't know the type of x until the function runs. It might be something different every time the function is called. Second, Python lets you override almost everything in the language with dynamic behavior, like descriptors, for instance, and properties. So we always have to check for these cases. And then even worse, anything can change at any time at runtime via patching. So even if we did know the type of x ahead of time, that wouldn't help because someone might have patched the type. So the next time the function is called, the type may have a new descriptor that it didn't have before. So again, we have to check dynamically every time, and this is slow. So we can add a second entry to our list of reasons why Python is slow. Everything is dynamic. We've been using attribute access as our example, but this applies across the entire language. We can have the same problem with function calls because we have to figure out what function are we calling, what method are we calling, what is its signature, what arguments does it take, and this all has to be figured out at runtime and slows the program down. Or we have the same problem with numeric operations. We have no idea until runtime, what are the two operands? How do we add them together? All of this is figured out dynamically. So the same problem of dynamic types and dynamic behaviors applies across every aspect of the Python language. So far, we've seen that we're making the CPU run more instructions to figure things out at runtime. But running more instructions isn't actually the root cause of slowness. A single CPU instruction can be almost free, or it can cost 10 or 100 times as much time as another CPU instruction. And the main reason for this, the key factor, is how long the CPU has to wait for the data that it needs in order to execute that CPU instruction. So the specifics here will vary some by the CPU model, of course, but typically a CPU will have 3 layers of cache and then main memory, main RAM. And it can often be roughly 100 times slower to fetch data from main memory than to fetch it from the cache. So what is going to be in your cache? Well, the things that will be in your cache are the things near or immediately following the data that you've already fetched. So this means that a key part of good CPU performance is having predictable memory layouts where your frequently used data is compact and contiguous and used in a linear fashion. What you don't want is for your hot data to be sparse, fragmented, randomly accessed. Modern CPUs do have lots of fancy tricks that they use to reorder and parallelize their work so that as much as possible they can avoid stalling out, waiting for data. But these tricks only go so far, so these are still important considerations for performance. So why is this an issue for Python specifically? Let's look at the memory layout of a typical Python object. Say if we just define my class and then create an instance of it and then assign an attribute to it. The memory layout for this object starts with OB_ref_count, which is just the count, an integer, the count of references to this object. And then when that count reaches 0, then the object will be destroyed or deallocated. Then we have OB_type, which is a pointer to the type object my class, which is itself a Python object with its own reference count, et cetera, et cetera. Then we have the dict slot, which is a pointer to a dictionary object, which has its own object header, and then a bunch of keys like foo and values like bar. But of course, the dictionary only stores pointers, so foo and bar are actually their own Python objects with their own object headers and everything. And all of these are separate Python objects stored at different places in memory and probably allocated at different times. So to do a single attribute load on a single Python object, we actually are pulling in data from probably at least 5 different Python objects at different places in memory. So now we've got our third reason why Python is slow. Everywhere you look, we're following more pointers to more different objects, which is not friendly to CPU caches. So these 3 is as far as I'll go right now for reasons why Python is slow. This probably doesn't cover everything, but I think it's a pretty good representation of the core issues. We've seen why Python is slow, but Python isn't the only language with these characteristics we've talked about. For instance, JavaScript is a dynamic language with many of these same characteristics. But recently we've seen very fast, high-performing JavaScript virtual machines. So can we use similar techniques to also make Python faster? Of course, I'm not the first person to ask this question. People have been talking about this for years. CPython, the reference implementation of Python that most of us use, was initially developed 30 years ago. There's been a lot of developments in the last 30 years in how to make dynamic languages run faster. So the first temptation people have here is, why don't we just rewrite a new Python interpreter from the ground up with more modern techniques? PyPy is the granddaddy in this space that many of you may have heard of. It's actively developed. It's almost 15 years old now. It's very usable, and it's faster than CPython for many workloads. There are also a litany of other abandoned Python rewrite projects, most of which I won't mention here, except for Sky Bison, which I will because it's the most recent and because members of my team worked on it. There's really one core problem that has dogged all of these rewrite projects, which is a problem many other languages like JavaScript don't have. CPython has an extensive C API that allows you to write Python libraries in C. And this C API can allow you to write very fast Python libraries like NumPy, which we just heard about, but it also exposes many of the internal details of the CPython interpreter. And so if you're going to write a brand new interpreter from the ground up and try to make it faster and more modern, you have to write an emulation layer for this C API so that you don't break all of these libraries. And it's very difficult to make this emulation layer both compatible and fast. The next category here is languages that achieve better performance by being almost Python, but not quite. So a classic example here is Cython, which takes a superset of Python syntax and compiles it down to C code into a C extension module. Another more recent example is MyPyC, which takes typed Python code and again compiles it down to C extension code. Or a project I work on, Static Python, which takes typed Python and compiles it to an extended Python bytecode, which can then run in an extended interpreter or a JIT compiler. All of these projects can deliver very impressive performance wins, but they have the downside that they're not quite Python. They're not quite fully compatible. And so this makes widespread adoption difficult. So the third category that's important here is people saying, well, if we're going to make Python faster, but we're also going to be compatible with the whole existing world of Python libraries and extensions, we have to just incrementally improve the existing CPython interpreter. So one example here is Piston, which is still actively developed and maintained by Anaconda. Another example is Cinder, which is the project that my team works on at Instagram. And then a unique entrant in this space, and the only one that's really gotten traction on making the core CPython interpreter that we all use faster, is Microsoft's Faster CPython project. So this is a very sort of brief and hand-wavy survey of the landscape, but many of these projects are all fundamentally using very similar techniques and approaches to deal with the problems that we discussed earlier. So rather than diving deep into one project, let's talk about the general techniques and approaches that many of them share. So let's go through all of our reasons we identified why Python is slow and talk about how we can address those to make it faster. I mentioned earlier that interpreter overhead is not really where we'll find the majority of our wins, but it came up first in our profiling, and it's pretty simple to talk about, so let's start there. Maybe the easiest way to understand this is to consider Cython, the Python to C compiler. So remember we looked at the core of the CPython interpreter loop, and we saw that it's just this big loop over the bytecodes with a switch statement for handling each bytecode. If you take a Python function and you compile it with Cython, without using any of Cython's special features or type annotations, what you will end up getting from Cython is roughly the same C code that the Python interpreter would use in this switch statement, but you'll just get it unrolled into a straight line C program instead of in a loop. So if the Python bytecode would have consisted of a load fast, and then a load adder, and then a return value, like our earlier sample function did, then the corresponding C function generated by Cython would essentially look like the C code for handling load fast, followed by the C code for handling load adder, followed by the C code for handling return value. So now, instead of going round and round the interpreter loop, we're just executing that same C code compiled in a linear way. And it turns out that this alone will usually make your code somewhere around 10 to 15% faster, which tells us that in Python, interpreter overhead is roughly 10 to 15%. So gaining 10 to 15% is great, but it's not really enough to make Python performance competitive with other languages. Let's also pause here and talk briefly about JIT compilation. That means just-in-time compilation, where while our Python program is running, we'll take the bytecode and we'll compile it directly down to machine code that does the same operations. Sometimes people talk as if JIT compilation is just magic magic speed dust. You sprinkle someone on your interpreter, and voila, it's fast. So speaking as someone who works on a Python JIT compiler, I can tell you this is definitely not true. If we build a very simple JIT compiler that just takes these same operations and compiles them down to machine code, just like Python, we'll gain 10 to 15%, but nothing more. So we need to use more advanced techniques in our JIT compiler if we want to really make it fast. So we can gain some speed improvement by compiling away interpreter overhead. But whether we have a JIT or Python or just the interpreter, to gain more speed than that, we have to look at our other problems, starting with the problem that everything is dynamic. So looking again at our very simple sample function, the problem we have here is that we have no idea what kind of thing x is, and it could be a different type every time the function is called. And this means we have to repeat a bunch of checks every time the function runs. We know nothing in advance about how to handle x.foo. But even though x could be a different type every time this function is called, in real-world Python code, it probably isn't. Most of the time, for a given function, its argument is going to be the same type every time it's called. And this turns out to be the key insight that lets us keep the dynamic nature of the language, but bring its performance closer to what a static language can achieve. So the insight here is that Python code can be extremely dynamic, but most of it is far less dynamic than it could be. So even though x could be anything on any call, we can gain a lot of speed back by taking advantage of the fact that in practice it probably won't be. So if we look back at this flowchart for x.foo, let's say that after our function is called several times, we see that it's always called with x being the type t, and that t does not define getAttribute or have a descriptor named foo, and it does always have a dictionary. So then we replace the generic loadatter instruction with a specialized one that just does this, and we skip a bunch of extra checks and just go straight to the dictionary where we know we're going to find the value of the attribute. Now you may be thinking this isn't safe, and you're right. Even if we saw many, many calls in a row where x is of type t, we never know if the next one could be some other type. So we have to add a guard, where first we check that the type is still the one we're expecting, and if it isn't, we de-optimize back to the generic version of loadatter. This guard check isn't totally free, but it's very cheap. It's just a pointer comparison. So now, in the likely scenario that our function is always called with a value of type t, we've won a lot of performance back. And if it's called with some other type, we'll still do the correct thing with not much slower performance than before. If you're really observant, you might think this still isn't safe, because remember that type t could be patched, and it could behave differently than the last time we saw that same type. So just checking we still have type t isn't enough. So we have to expand our guard. We can add a version to types and increment this version every time the type is patched. And so we can check if the version hasn't changed. This loses us a little bit because now we have to load the type object into memory to check its version. If we want to be even more efficient here, we can instead have a callback whenever types are patched. And when the type is patched, we can go out and find all the instructions that we specialized for that type and revert them back to the generic version. So that's another approach we can use. So we started using this technique in Cinder, our CPython fork, in 2019 with a catchy name Shadow Code. It, of course, handles loadatter, which we've been looking at, with 10 different variants of loadatter to handle all the different specialized cases that are possible. But the same specialization idea applies to many more cases throughout the language. Shadow Code also supports load global, store adder, load method, binary subscript. More recently, the faster CPython team has applied the same approach to the CPython interpreter in Python 3.11, with support for all the same opcodes that Cinder supports, plus a bunch more: store subscript, compare op, binary op, call, unpack sequence. So now we have some idea how we can handle Python's dynamism. We can take advantage of the fact that most code is not really that dynamic and specialize away a lot of the cost. So last, before we wrap up, let's look at our third problem, the layout of data in memory. Specifically, let's talk about how the attributes of a Python object are stored. For an illustration, let's say we have a simple person class initialized with just a name. So looking at this code, what attributes would you expect an instance of person to have? Just a name, right? Well, in Python, an instance of person can really have any attribute at all. We can always just tack on some random extra attribute in our code. And this is why historically Python has always stored instance attributes in a dictionary so that random new ones can just be added as new dictionary keys. But as we saw earlier, this is inefficient in memory usage, and it adds an extra memory indirection layer between the object and its attributes. So our key insight here is similar to the previous one. While it's true, technically, that Python objects can have any attributes, in practice, most of the time, they only have the expected ones for their type. Even though you can tack on random extra attributes, usually we don't. Usually all the instances of a certain class will share the same set of attributes. So how can we take advantage of this insight? If we look back at our Python object layout diagram, the first thing we should notice is that if most person instances will share the same keys, it's wasteful for every instance to have its own dictionary with its own separate list of the keys. It would make more sense to keep the keys just once on the class and have them shared between all the instance dictionaries. This is called split dictionaries in CPython, and it's actually been around for a while, since Python 3.3. At this point, we haven't reduced memory indirections, but we have reduced memory usage, which is also valuable. The next thing we can notice here is that unless someone actually accesses the dunder_dict attribute directly, which is not very common, there's really no reason we should even bother having a dictionary at all. It's just an unnecessary extra layer, so let's remove it. Now, in the common case, an instance just points to an array of its attribute values, and we know which attributes those are because the class keeps track of the expected keys. This change happened in Python 3.11. PyPy has already been doing something similar since 2010. In PyPy, it's called maps. So we can go beyond this. The next step to reduce memory indirections is to move those values directly into the object itself instead of allocating it as a separate array. CPython does not do this yet. The SkyBison interpreter I mentioned does do this. Possibly CPython will do this in a future version. Of course, since this is still Python, we still have to handle the possibility that someone might tack on a random extra attribute we aren't expecting. Some systems handle this by considering person plus extra attribute to be a new hidden class, or other systems might just tack on an extra dictionary when they need to in order to store additional unexpected attributes. So that completes our tour of why Python is slow and how it's being made faster. The good news for all of us is that so many of these improvements are now being brought upstream into the core CPython project, which means that all that you have to do to gain the benefits is to upgrade to a newer Python version. So thanks to the work of the faster CPython team, CPython 3.11 is somewhere between 25 and 60% faster than previous Python versions for typical workloads. And there's plenty more room for further improvement in future Python versions. I would expect another big speed up in Python 3.12 next year. Thank you for your time.
Thank you, Carl. So glad you are working on it, and most of us are not. I told you it was a hard problem. So, questions?
Oh, questions.
Back in.
Hello.
Hi.
One probably stupid question is that why? So in Python we have type hints.
Mm-hmm.
So when you are rewriting, for example, the load attribute, couldn't you use these type hints to know which function you need to call?
Yes, that is a great question. It's such a good question that I might have planted you in the audience to ask it. I didn't actually do that, but thank you for the question. So the reason that that isn't done is because type hints were added late to Python, and they were added in such a way that the runtime just ignores them completely. And they're only used effectively as a sort of a linter. So you can run mypy or pyr or some type checker over your code, and it will tell you if your type annotations are all consistent with each other. But when the code actually runs, nothing pays any attention to the type hints. And you can put in type hints that are basically just lies. And as long as your lies are all internally self-consistent, the type checker will be happy and you can go on. I mentioned a project in one of the slides in the talk called Static Python that I work on. And that project is doing exactly what you're talking about. So instead of ignoring the type annotations, in the Python bytecode compiler, we look at the annotations and we insert checks to make sure that at runtime, the actual type does still match the type annotation. And then based on that ability to trust the correctness of the annotations, we emit optimized bytecode that makes use of that type information to run faster. So static Python can achieve on some benchmarks like 20 times the performance of regular Python. But again, it has this cost that if you're going to adopt it in your code, suddenly you may find that type annotations that you thought were correct are not, and you have to fix them. So there's some cost to adopting it. But we are very excited about that approach.
Thank you.
Thank you. I think we had all right. Any other questions? I have another question there.
Hello, thank you. If the rewrite for Python is, let's say the main obstacle is the connection to C, can we either get rid of that connection and rewrite everything in Python, so it's done in Python everything, or have that C package as a standalone, let's say development by itself, where the update for that API connection is a standalone. We update this alone and we update this alone. Or the final solution is just give up and do the whole compiler in C++ or C#.
That's another excellent question. This is amazing. Yeah, I was just talking, so Travis talked about NumPy, and NumPy is a big part of the problem. Sorry, Travis. But we were talking just this morning about that very problem and some of the same solutions you mentioned, that if we can get more of what are today written as C extensions to be written in a higher level language like MyPyC or static Python or something, or if we can get something like NumPy and the other extensions to adapt to some kind of higher level API, then, as you say, we only have one place to update when the C API of CPython itself changes, and it's a much easier problem. That's great. I think that is the right direction, and people are working on that. The problem is it still leaves us with the problem of thousands of Python C extensions that exist today that do still have to be rewritten at least once to move away from the current C API. So that's still a big lift, but it is the right direction. Yep.
Yeah, another question. Just 1 second. Mike is coming. Thank you.
Hey, thank you for the wonderful talk. So this will be a quick one. You mentioned that in 3.11, the class objects, the dictionary has been removed unless someone's specifically wanting to use the dunder method.
Yep.
You also highlighted then that eventual goal, something you mentioned in your talk, is to move the variables directly into the object.
Correct.
By when do you see this happening, or is it already underway for 3.12? Just want clarity.
My understanding is that there is a hope to try to do this for Python 3.12. There are some complicated issues to work out around how exactly to do it and maintaining compatibility and making sure we don't waste memory by doing it. So there's some technical issues to work out, but I think the hope is to do it soon.
Great. Any other questions? One question right there.
A quick one. Thanks for the wonderful talk. Maybe a quick question. Is any of these Python rewrite trying to resolve the GIL problem, the global interpreter lock? Because that's the elephant in the room we never spoke about.
Yes, I didn't really talk about that. So the GIL, or the global interpreter lock, is what ensures that in a given process, only one Python interpreter can be running Python bytecode. This has some nice properties. It allows the Python interpreter to be faster because it doesn't have to deal with lock contention around shared objects. But the downside is it means that if you use threading with Python, you don't really gain any concurrency because only one of your threads can actually run Python code at a time. And this is, of course, a big problem for using Python effectively to take advantage of multi-core systems. There is a recent approach taken by a colleague of mine at Meta, actually, using something called biased reference counting, which I won't go into, but it helps deal with this problem of lock contention around the reference counts of shared objects across threads. And it looks like it can remove the GIL with only a very small performance penalty to single-threaded Python code, which is very exciting. There's still a huge amount of work ahead of us to get that work integrated. Part of the problem is this work was done on Python 3.8, and all of these other performance improvements I mentioned have changed the interpreter quite a bit between 3.8, 3.9, 3.10, 3.11, 3.12. So there's a lot of work to be done to take this no-GIL project and bring it up to date with the latest Python, and then merge it in. And then we still have the problem of all of the C extensions in the world which are not written to be thread safe. So it's a huge problem to deal with, but there are some promising approaches.
Awesome. Thank you.
Cool.
There are no more questions. Carl is going to be around, so if you want to ask questions later, come check it. Thank you so
Thanks,
much.
Fabio.
Great talk.